Welcome to The Explainer. Today, we are stepping into a high-stakes intellectual arena where a pretty radical new theory of the universe is being put to the ultimate test. So, get this. This is the fundamental question at the heart of the whole theory. And the panel that's been assembled to judge it, well, it's made up of some of the world's most brilliant and, frankly, formidable physicists. The stakes just could not be higher. And, just look at this panel. It's a murderer's row of physics. These are the heavyweights, the architects of our modern understanding of reality. And they are all here to interrogate one theorist, Doug Bundy, on his reciprocal system theory. So let's dive right into the cross-examination.
Okay, the interrogation kicks off with one of the most recognized figures in physics, Brian Greene. And he does not waste any time at all. He goes straight to the very core of Bundy's entire framework.
It's really the most basic, and yet probably the most profound question you could ask, right? If your entire universe is built on something called scalar motion, you better have a crystal clear definition of what that actually is. Bundy's response completely redefines our everyday idea of motion. He explains that, in the normal motion we're all familiar with, think of a car driving down a road, time just moves forward, but space just kind of changes its position. But in his scalar motion, both space and time are periodic. I want you to imagine a space clock and a time clock, ticking in this perfect reciprocal relationship. This, he argues, is the fundamental pulse of the entire universe. Okay, so with that basic definition on the table, another giant of the field, Leonard Susskind, presses Bundy on the next logical step. How does this abstract idea of motion actually create the tangible particles that we see and interact with every single day? So Susskind points to these core structures of Bundy's theory, things he calls the monad, dyad, triad, and tetrad. And he's really asking for the bridge here. How do these theoretical concepts create the very real physical properties of mass and charge that we can measure? So Bundy lays out this really fascinating progression. It all starts with what he calls the monad, which is just a simple universal expansion. And from there, complexity just starts building. The dyad introduces duality, things like expansion and contraction. The triad creates new combinations, which look a lot like photons. And then finally, the tetrad achieves the stable symmetry. And that's where the configurations that we recognize as fundamental particles finally emerge. It's like a journey from pure, simple unity to the diverse zoo of particles we know. And this totally reframes our entire understanding of these properties. If particles are just stable configurations of motion, then what in the world are mass and charge? According to Bundy's response to Susskind, mass and charge aren't these intrinsic properties that a particle just has. No, instead, they are the dynamics of the motion itself. Mass is simply a specific combination of different-handedness of 3D motion, while charge is just a direct result of the ratio between space motion and time motion inside that particle's structure. It's a radical idea. And right at this point, Edward Witten, an absolute master of mathematical physics, steps in. He picks up on this mention of 3D motion and asks a question that probes the very dimensional fabric of Bundy's proposed reality. Is time, just like space, three-dimensional? Bundy's answer is, well, it's really elegant. He says it's not that time is 3D, but that the dimensions themselves emerge, level by level, and they follow the beautiful mathematical pattern of Pascal's triangle. The monad is zero-dimensional, the dyad is one-dimensional, the triad is two-dimensional, and the tetrad is three-dimensional. The very structure of reality, he's arguing, is encoded in this ancient mathematical form. All right, now let's see how this framework actually builds the particles we know and love. Physicist Peter Woit, who's known for his critiques of theories that don't have testable predictions, he digs into the practical details of how this model accounts for the particles in a standard model. To explain all this, Bundy uses a simple but really powerful analogy, a seesaw. He says the combinations of motion can have more space motion, which tilts the seesaw one way, or more time motion, tilting it the other way, or they can be perfectly balanced right there in the middle. And here, Woit asks a crucial, clarifying question. Now, in mainstream physics, fermions are the matter particles, and bosons are the force-carrying particles. So he's asking if, in Bundy's system, the things that make up matter are actually built from the things that carry forces. It's a wild idea. And this chart here brilliantly illustrates Bundy's response, which was simply, exactly. You can see how it all fits together. An electron is just a configuration with more space motion on all three axes. A positron is the complete opposite, with more time motion. A neutrino? It's perfectly balanced. And the quarks? Well, they're the mixed combinations, which Bundy adds is actually what accounts for their mysterious color charge. Okay, so the panel's questions now expand in scope. They start connecting Bundy's microscopic theory of particles to the largest scales of the universe and some of the deepest paradoxes in all of quantum mechanics. Physicist Lee Smolin poses a fantastic question. If photons are made of combinations of these pulsating, basically stationary points, how on earth do they manage to travel at the speed of light, the cosmic speed limit? Bundy explains that it's all in the combination. As you can see in this diagram, when you combine the two types of pulsations, the inward pulsing parts basically cancel out, and that creates the photon's internal oscillation. You know, its wave nature. But the non-pulsating parts, they combine to create forward propagation. It's this beautifully simple mechanism for generating motion from what is essentially stillness. So when Witten asks him how his theory compares to string theory, Bundy points out a really key similarity. Both theories get rid of the problematic point interactions of standard particle physics. But then he highlights one massive difference. String theory requires 10 or more dimensions to work. Bundy's theory, he claims, does all of its magic in the familiar 3 dimensions of space and 1 of time that we all experience every day. To wrap up this incredibly intense cross-examination, the discussion takes a really fascinating turn. It looks at the philosophical and even the ancient historical roots that are underpinning Bundy's very modern-looking theory. And then Bundy reveals that his entire model, from the monad all the way to the tetrad, is structured on the Tetraktys. Now, this was an ancient Pythagorean symbol that represented the pathway from unity to complexity, from a single point to a 3-dimensional solid. He basically found a modern key in an ancient idea. So, what's the crucial point here? Bundy's final argument is that mainstream physics, by focusing only on vector motion, has completely overlooked an entire aspect of reality. He believes there's this hidden world of scalar motion, with its own dimensions and polarities, and that understanding it is the key to unlocking the universe's deepest secrets. So ultimately, whether Bundy's reciprocal system theory is right or wrong, this whole intellectual gauntlet forces us to ask a really profound question. Is it possible that our fundamental assumptions about space, time, and matter are just one way of looking at things, and that a completely different lens could reveal a reality we never, ever imagined?